So we talked about those things. First we talked about system, then we discussed what are surroundings. Generally, although everything out of the system or everything except the system is taken as surrounding, but generally you say that surrounding would be related to those things which are going to affect the system. Okay, I gave you one example that if I am talking about an academic performance of the academic performance of one boy, so I would say that he is going to affect its performance, not that boy. Why? Because he is not directly related with him. Okay, so although he is a surrounding, but still you can only take those objects as surrounding, which is basically going to affect the performance of the system. And then we talked about control mass, the closed system, and then control volume, the open system, and I also told you something about control surface, which is basically a demarcation between the system and the surrounding. Okay, so these are few terms because we are just on the very first chapter. This is kind of the second lecture, you can say. So we are just trying to understand what kind of terminologies we are going to interact in this subject. Okay, so these are few terminologies. I would also try to define few other terminologies, so you should understand what the definition of these terminologies are. Okay, and then we would look about the applied side later. Okay, so for the time being I am just trying to describe all the definitions. So let's start. There are few other things which I am going to describe now. Have you ever heard about anything like macroscopic or microscopic? Okay, so generally whenever you talk about thermodynamics or behavior of the materials for any scientific field, these are two approaches, macroscopic and microscopic. Okay, and this macroscopic and microscopic approach, there is a difference. And the only difference is, which is basically a huge difference, that one approach considers the structure of matter and the other approach does not consider the structure of matter. Structure of matter means molecular structure, how atoms are interrelated with each other and all that. But if you do not consider the structure of matter, it means you are talking about macroscopic property, and this macroscopic property or behavior, it gives you the overall behavior of the system without considering the molecular structure. Okay, and if you consider this macroscopic approach, you will talk about classical thermodynamics. Yes, in macroscopic approach you do not consider the structure of matter. Okay, in microscopic approach you do consider the structure of matter. Okay, and this microscopic approach is as if you are considering all the molecules as few particles. Okay, you consider their behavior and then you take out the average of them. Just like, for example, just consider what is the velocity. For example, I say that. So you would consider the velocity of one molecule, you would consider the velocity of the other molecule, and all, let's say 10, 14 molecules, and you say that this is the average velocity. Okay, so this kind of approach is taken in statistical thermodynamics. Statistical thermodynamics. Now, statistical thermodynamics considers this structure of matter. You consider all the quantities at the while going at the molecular level, and then you talk about that macroscopic property. You might have heard about something like continuum. Have you heard about it? Ideal gas law in your chemistry course or physics. Continuum. You treat every solid object as a continuum in engineering. You treat every fluid object or fluid, you can say, body as a continuum. So you say that you don't need to go at the molecular level, you would look at the overall behavior of the system. Okay, overall behavior of the system. For example, if I ask you, how would you define density? You would just say that it is mass per unit volume. Okay, it's a very layman's definition, but for example, if I ask you to find out density at this point, if the temperature of this point is higher, obviously its density would be what? Okay, if you go to the other point and you take its density over there, you measure its density over there, it may be different from this point. You understand that? But if you say that this is the density, would it mean that these are the molecules which are showing that density value? Not at all. What you would be seeing at, you would be looking at few, let's say, few number of molecules, just a spatial point, or you can say you are looking at a very small area, and based upon that small area which might have been containing millions of molecules, right, and you say that, okay, fine, this is going to be its density. Okay, and if you have a certain number of molecules, I think you might have heard about this number, Knudsen number. Okay, just write down this term, Knudsen number, go back, Google it, and see how does it define continuum. Okay. So continuum is something which is basically giving you the overall behavior. For example, if you just look at this blackboard, it looks like a continuous media, right? You cannot define that this is molecule number 1, this is molecule number 2, this is molecule number 3. You can't define it. Okay. So if you are looking at it from a broader perspective, so overall behavior is kind of as if it is a continuous media. Okay. You are not looking at discrete molecules. By the way, this number would try to help you understand what that actual definition of continuum is. Okay. So I was talking about this macroscopic and microscopic property. Then whenever you talk about the statistical thermodynamics, what you do is you talk about average properties of molecules, and then you try to relate it with the overall behavior of the system. This is how you do things in statistical thermodynamics. Okay. Now, this statistical thermodynamics is very important in the field of high speed flows which are related with gas. You might be looking at chemical kinetics. Chemical kinetics means how those molecules are basically interacting with each other, how those forces are there, intermolecular type of forces. Then if you talk about lasers, plasmas, I hope you remember the jumping of those molecules from one energy level to the other energy level, and then you talk about the overall average stuff. So again, you go to the molecular level, so that's why it is related with statistical thermodynamics. Then if you talk about very low temperature applications, and generally those materials which are basically dealing with very low temperatures, these are known as cryogenics. Just remember this term, cryogenics. And there are other things as well. By the way, this is also needed to define ideal gas law. Do you remember that? Is it the ideal gas law? I hope so. So these are few applications of classical thermodynamics. Generally we don't deal with this kind of thermodynamics at undergraduate level. Okay, this is statistical. This is related with statistical thermodynamics. These are the applications. Okay, we don't deal with this class. We would be dealing with the conventional classical thermodynamics. Yes, the difference between them is you talk about the overall behavior. Let's say, if again I would give you the example of this class. For example, if I look at the overall behavior, I would say that okay, there is a general perception that this class is a decent one, for example. And if obviously in a decent class you may have some bad guys as well, who are not interested in academia, or let's say who are always trying to involve themselves in mischievous activities. So I can just say that. So it's a general perception, and then if that general perception is not based upon, you can say, overall by taking the average, okay, this behavior plus that behavior divided by 48. Not at all, right? So it's a general perception, overall perception. I would consider that as if you are behaving as one unit, and then I would develop some perception about you guys. Okay, but otherwise, if I go for the quantitative detail, what I would do is I would say, okay, fine, let's talk about their individual behavior, then sum it up, then divide it by 48, and then see whether my overall perception was related with it or not. Okay, these are the two things which I wanted to talk about. So statistical thermodynamics. Now by the way, in classical thermodynamics, we also would not consider relativity effects. I hope you understand how energy is transferred into mass and mass into energy. So we won't be looking at that. This is kind of some other topics related to physics. So let me define some other things. Property. So definition of property is a macroscopic characteristic of a system such as mass, volume, energy, pressure, and temperature. There may be other things as well. I am just writing a few examples, to which a numerical value can be assigned without knowledge of the previous behavior, or you can say history of the system. Like for example, if I want to estimate what is the temperature at this point, I don't need to see what was the temperature during the last night. I can just put a thermometer over there and I can come up with the temperature value. So a numerical value can be assigned to that. Okay, similarly you can find out density, similarly you can find out pressure and all the other things. So this is something which is a traditional definition of property. Now there is a term which is known as state, right? So you can say it's a set of property. It is a set of properties. No, in properties you do not need to consider those. Just look at the definition. which can be assigned without knowledge of the previous behavior. I mean, if I want to measure this temperature, I don't want to consider what was the temperature 2 days before, 3 days before. This is just kind of instantaneous value. It can be assigned, a numerical value can be assigned to that. So a set of properties. So you can say for example, a set of properties means what? I mean, you define some temperature, you define some pressure, you define some energy, and you say that this is one state. Okay, you can add some other properties as well. And similarly, if you go for some other point, you can define other states. You would say this is point 1, so it is having a pressure of P1, T1, and then you go to the other point, you say that it is having a pressure of P2, T2, right? So these are basically what? Sets of properties which are defining states of two systems. Okay, so whenever you talk about state, it means it's a set of different properties. Now let's define something about process. When any of the properties of a system changes, obviously the state would change. Why? Because the state is kind of a set of properties, so if properties change, state would also change. So the state changes and the system is said to undergo a process. Okay, I hope you understand. It's a very simple thing. If state changes, if properties changes, it means it has occurred due to some process. That process may be anything. Like for example, you might be heating an element. You just put, let's say, a lamp over there, and you would see that the temperature of this point would change. It means it has undergone a process, right? So whenever a state changes, it means it is a process. Now, if during any process the state does not change, during any process, if a state does not change, it means your system has achieved a steady state value. Now there is another thing which is steady state. What do you mean by a steady state? A system is said to be at steady state if none of the properties change with time. Okay, now how can we define it? No, they don't change. They don't change. If they went back to the original system, that is something which is related with stability. That's altogether a different thing. Okay, that is something which is related to dynamics and control. I'm not going to comment on it, but this is steady state. I would show you one example as well.
So are they not changing with time, or are they not changing
with time? I mean with time. Yes, with time they are not going to change. Okay, so let me give you one example. For example, you just measure a temperature at this point, and you say that, okay, I have time with seconds over there, and then I have temperature in degrees centigrade along y-axis, and at 1 second, let's say I measure my temperature, it is something over there, then it becomes this, this, and finally as the time proceeds it stays at a constant value. You see, after some time there is no change in temperature with respect to time. So what does that mean? That the system, which is basically this point or these much of let's say number of fluid particles, they have achieved steady state in terms of temperature. So whatever the process is going on, the heat is coming in from outside, still this is not going to change, right? So this is something which is known as steady state. Just like, for example, if you would come up to a conclusion that if you have a CGPA, so if you settle your CGPA within first 2 or 3 semesters, it won't change much after, let's say, 3rd or 4th semester. It won't change much. It means you would be achieving kind of a steady state, right? So these are just few examples. You can't say that the process is okay, fine, no problem at all. We are not defining that steady state with respect to a process. We are defining it with respect to change in the state, right? And obviously a system is set to undergo a process if its states change. Okay, so that was what I need to say about steady state.
Can you give us a
Mechanical
mechanical example of steady state?
example of what?
Steady state.
Yes, just talk about an aeroplane. During takeoff, its elevation is changing, and once it is at a level and it starts cruising, it means it has achieved its steady state with respect to height. And same is the case for, let's say, if you are driving car at a certain velocity, right? So if state is not changed, velocity is not changed, let's say, so it means this is what? It's a steady state. Sorry? I don't think so. I don't think so. Why? Because it's acceleration. If you talk in terms of acceleration, yes, it depends on the parameter as well, which state you are measuring, right? So in thermodynamics, we generally talk about temperature, pressure, energy, and all this. We don't talk about velocity, acceleration. Okay. Then there is one more thing about the types of properties. There are 2 types of properties. So extensive or intensive properties. These are 2 types of properties for thermodynamic studies. Okay. A property is called extensive if its value for an overall system is the sum of its values for the parts into which the system is divided. It means if I am just looking at the complete volume and I say that I divide that volume into 10 pieces, and for example the whole volume of the system is basically sum of the volumes of those 10 pieces. So what does that mean? This is basically an extensive property. And similarly, if you consider about the mass, for example, what is the mass of this class, let's say. So what I would do is I would consider the mass of all the individuals and then add it, and then I would say this is something, the mass of the total class, right? So that is what? That is the extensive property. If you divide the whole thing, whole system into small particles, small subsystems, and then you add all the properties of those subsystems, and finally by addition you come up with the property of the system, total system, you say that it is an extensive property. Just like that, example, just consider, I say that this is one box and I divide it into, let's say, few number of boxes. I ask you what is the area of this system. Let's say this is my system. What is the area of this system? Obviously what you can do is you can go back, find out the areas of all those 9 boxes and say that addition of those areas for those 9 boxes would give you area of the total system. So what that area is, it's an extensive property, right? Similarly, mass is an extensive property. Similarly, volume is an extensive property. But if I talk about temperature, would you say that temperature of this system would be equal to addition of all the temperatures of these 9 objects? Not at all. So that temperature would be an intensive property. Okay. So similarly, let's define that intensive property. Intensive properties are not additive. They are not additive. It means you can't add the temperature of the components of the system and then say this is the total temperature of the system. You can't do it. Okay. The values of the intensive properties of the size or extent of the system and may vary from place to place, just like you consider temperature at this point and temperature at the other corner of the room. So it may vary from place to place within the system at any moment. Okay, so at any moment you can see that temperatures it's changed. So what you see is that this intensive property, if I say that, for example, this small p is my intensive property, so it can be a function of space and time, right? It can be a function of space and time. So by writing this x, I am just talking about the whole spatial variable x, y and z. This is kind of capital X, so I can say that this is small x, y, z. Okay, so you can say that this intensive property is a function of space and time. Examples are pressure, temperature. What about density? Okay. What about energy? Energy is an extensive property. Okay. Sorry? Now, let's talk about the other things. Equilibrium. You might have heard about it, equilibrium, right? So in mechanics, what you see that this equilibrium is related to something where yes, I can't use the word stable. Stability is something else, equilibrium is something else. For example, if I say that you are applying some force on this object over there and you are applying the same force from this direction, and if those two forces are equal, that body would be in equilibrium, right? So this is what you see in mechanics. But in case of thermodynamic equilibrium, it is kind of, you can say, a wider terminology. It has its wider application, right? Although it goes into the same sense, but let me define thermal equilibrium first. For example, this is a hot object and this is a cold object. For example, these are two objects. And once they come into contact, what would happen? Heat would flow from the hotter object to the colder object, right? And then finally, what you would see is that temperatures of both the objects would become same. At that point, you say that both the objects are in thermal equilibrium. Okay? So, till the time heat is being transferred from the hotter object to the colder object, you would say that the process is kind of non-equilibrium. Do you understand that? That the process is non-equilibrium. So just remember these words and you tell me, heat transfer, is it an equilibrium process or a non-equilibrium process? It's a non-equilibrium process. Why? Because it would happen till the time your bodies would become in thermal equilibrium, would come to a thermal equilibrium, right? So thermal equilibrium is something when you do not allow any kind of heat transfer from one object to the other. Okay? So similarly, you would talk about few other types of equilibriums. That is mechanical. Obviously that mechanical equilibrium is related to the forces and torques. And then this is phase equilibrium. I mean, you might have been looking at those vapors coming out of some fluid object, fluid vessel, and then you would see that some vapors would be going inside as well. Okay, so it is kind of recirculation. I won't talk about that much, but for the time being you can just understand that this is something which is related to phase equilibrium. Then there is something related to chemical equilibrium. Okay, chemical energy going over here and there. So these are the four types of equilibrium which are generally considered in thermodynamics. In the field of mechanics, you just consider equilibrium with respect to forces and torques, which is basically sigma f equals 0 and sigma tau equals 0 on an object if you talk about a static equilibrium, and they would become MA, and similarly it would become I alpha if you talk about dynamic equilibrium, right? So thermodynamic, you can say it's kind of dealing with all those four kinds of equilibriums, right? So I would leave some points for you guys, okay? And I won't be, because within those lines you would see much of the information. I am giving you few prominent points. I am just trying to describe few terms, just trying to make you understand what are those terms, what are different examples related to those terms. But within those lines, it's a hell of information. Okay, go back, read those lines. Okay, so then let's talk about units. Why? Because we have talked about extensive property, intensive property, and you have seen that we are going to associate a number with that property. Okay, and obviously if we are associating a number with that property, it means we have to associate a unit with them as well. Why? Because it's a physical quantity, so it needs unit for the complete description. So let's talk about unit systems. You are well versed with those unit systems. You know, we generally deal with SI unit systems and then English unit systems. Now, most of the time, people deal with SI units. If you go to the industry, you would see that they deal with SI unit system. But in many of the countries, just like USA or UK, they prefer this one, English, right? So you have to be well versed with both of these systems. I would just give you few examples. I hope you understand what those primary dimensions or the base units are. You understand that? What are those base units? Generally in mechanics you deal with length, mass and time. These are what? These are the base units. Why? Because all the other quantities, just like force, pressure, velocity, acceleration and all other things, they are derived from these three base units. Till the time you go for some other field, for example you go to electricity, then you need to define electrical current. Okay, so these are the things. And similarly if you go to thermodynamics, you need to define temperature then. So temperature would become a base unit in the field of thermodynamics. Okay, so you know what is base unit. These are few quantities. Generally I think maximum number of base units are 7.
Yes.
Right? So candela, it's the quantity of light, and then current, and there are few other things. So 7 quantities are there, and you can derive all the other quantities from this one, from these, right? So I won't be discussing those SI units and English unit systems to a great extent, but because you have already been introduced with them in your earlier classes. So please go back and see. And the most important thing is you should be able to convert a quantity from one unit system to the other one. Just like you should be able to at least know, for example, how many pounds are there in 1 kilogram, or let's say how many kilograms are there in 1 pound. Similarly, you should be able to see, at least you should be able to understand what those conversions for base units are. Let's say you should be able to understand how degree centigrade can be converted into Kelvin, or let's say Rankine, or then Fahrenheit. You should be able to do it. And you should not be able to, I think you should not be looking for help from the book all the time, or let's say at the back side of your calculators to do that conversion. It should be in your head. Okay. I would talk about those units for temperature after a short while, but just remember that for temperature we have 4 types of units. In SI units we deal with kelvins, because this is something which is the most important one, then degree centigrade, degree Fahrenheit, and then we talk about Rankine system, right? So these are the 4 quantities which we deal with in thermodynamics. Okay?
All these are SI units?
No, all these are not SI units. This is the SI unit. All they belong from different unit systems. Okay? Rankine. I would define them. After a short while, I would define all those quantities. Now, let me define few other quantities as well. Did you hear about this term, specific volume? Generally, you can say it's a reciprocal of density. I'm just using a small v, smaller v, right? So you can say it's a reciprocal of density. So let me define density from an engineering perspective, and then we would see what that specific volume is. All you know about density is it's a intensive property or extensive property. It is an intensive property. Okay. Now you can say that I would define density as limit v approaches v bar m over v. Now what does that mean? I mean, that means is that if you look at gas or fluid, any kind of liquid, it is really hard to isolate a particle from the rest of the system. It is really hard. You can't look at one molecule, you can't look at one particle and then you say this is the density, this is the pressure. So what you do is you mark an area, you mark a small area, a very small area, which is basically being represented as V bar, and you say that this is, although it's a very small area, but you can also say that it's kind of a point. If you look at it from overall, it looks like a point, a very small area. Okay, so that's what limit describes. For example, if I say that there are, let's say, this much of mass within that small volume, then I would say this is density. Okay, this is what technical definition of density is, and what I'm assuming that this system is behaving as if it is a continuum. It's a continuous media. It is not a summation of few particles. It is just behaving as if it is a continuum. Okay.
Can you explain how does the limit V versus V bar, because you just define V bar as that small little space?
Yeah, I mean, if you go, just consider that this is the complete volume, for example. Okay, fine. I say that I want to find out density. What I would do? I would say that, okay, a very layman's concept would be find out the mass, find out the total volume, and then say this m over v is density, right? But generally this is not the case. I mean, if you look at it from a mathematical point of view, you need to describe density. And what you can see is you have already understood that this density is an intensive property. I mean, it should be defined over a point. Do you understand that? So you won't be looking at the whole volume. You would be coming into a small volume which is basically looking like a point. Do you understand that? So if it is looking like a point, assuming that it is a continuous media, it's a part of a continuous media, you say that this whole volume has basically approached to a small v dash, and then you say that, okay, this small v dash is having this mass. Then you say that this m over v, I've already explained what limiting case is, and then you say this is density. Do you understand that? So that is something related with the intensive property. That's what you define at a point. Although it is not actually a point, it is some area, some volume, but it is very small, so you can consider it as if it is let's define mass then. Mass associated with a particular volume of V is determined in principle, I am talking about the mathematical principle, by integration. So you won't be looking at that m equals rho into v, you would say that m is equal to integral rho dv, and obviously you are integrating on the whole volume. Okay, so this density is what? This density is a function of do you understand that? So that's how, and obviously you can write this dv as dx dy dz. So that's how you can integrate for the first time, then integrate for the second time, then integrate for the third time. Okay, and come up with the total mass. So that's how you do it if that is, you can say, non-uniformly distributed. So this is the actual definition of mass. Then the specific volume, I have already told you that it is something which is reciprocal of density. So what you can see is this is giving you volume per unit mass. I am talking about specific volume. Okay, so this is volume per unit mass because it's the reciprocal of that density. And then in certain applications you also talk in terms of moles. I hope you understand what those moles are. Mole. Okay, what is a mole? I mean, what's a mole? You should be able to understand it. Representation of molecular weight of an element or a compound of a chemical species in grams or kilograms, something like that. And you might be describing those things in pounds as well. Okay, so if you represent the molecular weight of a chemical species in grams, kilograms or pounds, you would say that you are describing it as if it is 1 mole. And I hope you understand what that Avogadro numbers. So please go back, see that number. How is it related with mole? Okay, so I would just be floating few kind of reading assignments for you guys as well, right? So Avogadro's number, just go back. I hope you understand it. And then you would be able to try to relate it with mole. So how you can define it? If I ask you how many moles are there in certain number of kilograms, you can use this relationship, right? So this is the molecular weight, and then this is the total mass. You can see that it is the number of moles. And please remember, we can define it in terms of grams, in terms of kilograms, and then in terms of pound force. Okay. Let's talk about a very important quantity which should be able to understood, that is pressure. So that pressure is, this is pressure as a, let's say from a very simple concept, how do you see pressure? You say that pressure is force per unit area. And for example, okay, this is pressure, force per unit area. We are more concerned with fluids. We are more concerned with fluids which are related with liquids and gases, both of these species. We are not concerned with solids. Generally, thermodynamics, in thermodynamics, we look at those behaviors. So, just see that if a fluid is at rest, for example, this is a vessel. If a fluid is at rest, I pick a small piece of volume. Let's say I pick this small piece. This becomes my system. I should have drawn a dashed line, but just consider this is my system. And I say that, okay, this is my system. If I say that this fluid is at rest, this fluid is at rest, some force is being applied from its upper side, some is being applied from its left side, right side, and then bottom side. Do you understand that? And this small control volume, or let's say small piece of volume, that is something which is in equilibrium. What kind of equilibrium it would be? Mechanical equilibrium. Why? Because I am talking about the net force. Net force is kind of 0. So if I make this area very small, if I ask you find out the pressure at this point, for example, what would you do? You would try to reduce that area, and you would go up to an extent where you say that, okay, fine, this is a very small area which is describing that point. Okay, so what I would say is, that I am saying that this limit area approaches from A to A bar, which is describing a very small area. Obviously it is composed of so many molecular particles, but still I would treat it as if it is a point, and alongside it is a very small area. I would say that this limit is equal to pressure. This is the actual definition. Okay, so that you can define pressure at a point. Otherwise you should have defined pressure for some complete area. You won't be able to define pressure at a point. Okay, but in fluids you need to define pressure at a point. So to define it, to apply it on that point, we need this definition. You need to understand that it is not all about force over area, not at all, right? It is something which is a limiting case coming from a larger area to a very small area, and then you should be able to mathematically apply it. Okay, what? No, I'm still discussing that pressure. I would talk about its different components. Just let me complete my discussion and then I would come to your question. Okay. So you can say that this area, this A bar, is kind of area for this very small point. Okay. If it is at rest, what you would do? The net force would be 0. The net force would be 0 because it is having similar forces, same forces from opposite directions, and that's why it is at rest. So you can say there is a huge conclusion. Remember that you would also use it in your fluid mechanics course. Pressure at that point, which we were talking about as A bar area, is the same in all directions as long as the fluid is at rest.
Within the system.
Yes, within the system, obviously. No. Do you associate anything like direction with pressure? Right? Yes, obviously the fluid is at rest means the whole fluid body is at rest. It is not moving. It is not a river. We are not talking about any kind of ocean. It's something which is being placed in a vessel. Right, and you can also say that, okay, fine, let's talk about fluid in a dam. It looks like a stationary body most of the time. Okay, so that's what you say. A macroscopic approach. Obviously, molecules won't be stationary at any time. It would keep vibrating. Okay, so that's what I have already defined, that we would be taking all the things as if they are continuum, and we are treating them from the perspective of classical hydrodynamics. Thermodynamics. So there is another point. Pressure is an intensive property. So it means pressure is a function of space and time. A very good example could be, if you look at pressure, and this is basically elevation. Let's say this is y and this is ground x, and I'm considering as if I'm on a ground at x-axis, and this is elevation in, let's say, meters or kilometers. If you go up, what would you think? Pressure would change? You might have heard about it. Pressure would change. I mean, pressure decreases as you elevate yourself, right? So if that pressure is decreasing, it means it is basically what? A function of space. Do you understand that? If you have an experience of traveling in an aeroplane, you would see that if it is climbing, what would happen? You would see some kind of activity in your ears, and it is due to what? The change in pressure, right? So similarly, if you travel on motorway, for that color kahar area, you would see that there is some kind of activity going into your ears. What is that? That is due to pressure, change of pressure, right? So you would see that as if your ears are opening and then closing. So that is something which is related with pressure. At different times, you may have different pressures. I mean, just look at that. For example, you might be looking at wind. If the wind is blowing, it means that wind is traveling from one area to the other area, and obviously that wind would be traveling due to what? The pressure difference, right? For example, if the pressure becomes low in this area, obviously the wind would start flowing from the other areas towards this area, right? So that's how you can have hurricanes and then rain and all that. So the thing is, how do you find out pressure? There are three terms related to pressure: absolute pressure, then we have atmospheric pressure. Atmospheric pressure, I hope you understand, this is something which is there in the atmosphere. The air is applying that much of pressure on your body, on all the bodies, and generally that pressure is taken as 1 atmosphere. The unit is atmosphere. Generally it is represented as 1 atmosphere. You know, it is also written as what? How many pascals? Okay, 101,325 pascals or Newton per meter square, right? That's what you can see. So anyways, this is atmospheric pressure. Now to measure pressure, simplest techniques would be related to manometer or barometer. Manometer or barometer. Okay, so what that manometer is, for example, you have a tank with you, it is a closed tank. This is how this device is working. I mean, at this end you would have air which is applying P atmosphere. At this side, let me show you a small chunk of volume there. I mean, this is the column of that liquid which is over there, right? And this gas is basically at a uniform pressure of P2, for example, right? So, and obviously I would say that this P2 is being taken as P absolute, you can say. Okay, now fine. Now see, at this end, if I talk about pressure at this point and pressure at this point, they are at the same height. So those two pressures would be same. Those two pressures would be same. So it means if this length is L, so I would say just try to, what is the pressure at this point? P2 or P absolute? Right? So if I say that what is the difference between P2 and P atmosphere, that would be equal to something which is a function of this length, right? And that something is basically defined as rho GL. That something is defined as that rho GL. So I can say that P absolute of this gas inside the tank would be equal to P atmosphere plus rho GL. Okay, so this is how you define it. If you talk about principle of a barometer, this is basically working of a manometer. Similarly, you can talk about barometer. you have a column over there, a small tube, and then you say that there is some kind of mercury or other objects over within that. If I talk about pressure at this point and pressure at this point, what would you say? These two would be same. So okay, fine, this pressure would be equal to P atmosphere, this pressure would be equal to P atmosphere, obviously because atmosphere is around this object, water body, but there would be few vapors within that empty space, isn't it? Few vapors. So I would say that this is basically vapor pressure, that pressure which is being exerted on that fluid body inside that tube by those vapors. So obviously this length would be equal to L, let's say. So what I would see, if this mass of this body, this fluid body, density of this fluid body is rho m, so what I would see, what would be the difference between P atmosphere and P vapor? What would be the difference? Right, that height, something a function of that height, and what that function is, that is rho m gl. Rho m means I am talking about density of this mercury. Generally it's mercury, so that is why I am just representing it as mercury. Right, so you can say that in this case P atmosphere would be equal to rho vapor minus rho m gl. This is how you measure pressure through a barometer. Oh, I'm sorry, yes, it should be added. And sometimes you describe this pressure in terms of length of mercury. That's what you say, that this is millimeter of mercury. I hope you have seen this unit for pressure, millimeter of mercury. So what does that millimeter of mercury is? This is basically related with that length. Okay. No, rho vapor means because there would be some pressure, so some vapors inside this empty box. Generally there is mercury inside this body. So because there are mercury, so mercury basically it evaporates, and obviously if you put it in an inverted way, so that those vapors would obviously exert some pressure on it, right? So that's how it is defined. So please go back, and I would just write down few more things. Just go back and check those devices, how they work. Bourdon tube gauge. Just see this one. How does it work? Okay. Oh, I'm sorry. This is P vapor. I'm really sorry for that. This is P vapor. Obviously, this is just about these pressures. You take it on this side and you say it is P vapor. This is rho. Yes, this is rho. Okay, just let me write it down clearly. So P atmosphere would be equal to P vapor minus rho m gl plus, yes. Okay. Right. So please go back and check this Bourdon tube gauge. It is given in one of the books, reference books, and then you can also Google it. Okay. Just see how those things are being measured. Right. The last thing which I am going to talk about today, it is buoyancy. I hope you understand that. What is that buoyancy? If you submerge some object inside the water body or inside a fluid, it would try to go up. Right, so this is something which is related with buoyant force. So from Archimedes' principle, that buoyant force is equal to, basically it has a magnitude of the weight of the displaced body, weight of the displaced fluid by that body. Okay, this is the buoyant force. So let's understand this from one example. Okay. Done? Okay. So just consider that there is a water body. No, weight of the displaced fluid. For example, if you just put that much of object inside the water body, it has got some volume, and you would multiply that volume with volume with what? Rho of the fluid. Rho of the fluid. That's what Archimedes' principle is, to find out the total buoyant force. So, for example, if I say that this is the water body, or let's say any fluid body, and then you place some object over there, I say that what is the total net force being experienced by this object? Let's say this height is L1 and this height is L2, for example. Obviously at this side you would have pressure atmosphere. Okay. So on this side, force would be equal to what? P2 into area. Just if I write it down from overall behavior, force on this side would be equal to P1 of area. What would be P1 at this point? Atmosphere plus rho g L1, right? And what that rho would be? Rho of the fluid. Similarly, P2 would be equal to what? P atmosphere plus rho g L2, right? So what would be total buoyancy force? I mean, this would be equal to P, because buoyancy force would be lifting that body in the upper direction. So I would say that this is P2 minus P1 into A. Area would be same on both the sides. I am just talking about a rectangular object. So what would you come up with? You would say rho g L2 minus L1. And what that L2 minus L1 is? This is basically length of this body, isn't it? Right? So this is the volume of the object, volume of the immersed object. So you have come up with the same conclusion from the Archimedes principle. You have seen that it is basically equal to, buoyant force is equal to what? It is related to rho of the fluid, and then g, and then it is being multiplied with the volume of the object, the displaced volume. Now just one quick comment. I am just talking about these two terms because it is related with pressure. P gauge is equal to P atmosphere. Okay, P gauge is equal to P absolute minus P atmosphere. Generally you use this gauge pressure term when pressure of the system is greater than the local atmospheric pressure. I hope you understand what do I mean by local. Local means at that point, at that location. So if pressure of the system is greater than local atmospheric pressure, you would use the term gauge pressure for their difference. Similarly, when local atmospheric pressure is greater than the pressure of the system, you would use the term for their difference as vacuum pressure. Vacuum pressure. So you can say P vacuum would be equal to P atmosphere minus P absolute, or you can say pressure of the system. Okay, these are different quantities which you use it over there. By the way, those derivations are given in your book. You can just see it. It's a small thing. You are done with that? Okay, so whenever you describe pressure, you should be able to understand whether it's an absolute pressure or it's a gauge pressure. Okay. So that's all from my side for this lecture. Let's meet on Monday, inshallah.